Okay, good morning. So let us start this last part of this chapter, which is a very important lesson called mathematical induction. That is a very strong method for proving statements which are related to natural numbers only. Okay, so let me just read it for you. Let P of n be a statement regarding the natural number n. In the book, the natural number starts from 0, 0, 1, 2, 3. I will always follow that natural numbers start from 1. So in the book, they have written P of 0 first. But I have written P of 1. Okay, so let P of n be a statement regarding the natural number n. The starting point is number 1 with two properties. The first property is that if you check that statement for n equals to 1, you realize it becomes a true statement. The second part is that if you choose a natural number k and assume that p of k is true, so you see it's different. You're assuming that p of k is true. If you find a way to show that p of k plus 1 is also true, then in principle you can conclude that P of n is true for all natural numbers, yes? Because you check that P of 1 is true, and you, in the second step, you prove that if P for a number k is true, P for the next number k plus 1 is also true. If you think a little bit more, it will actually it tells you that P of n is true for all natural numbers. Why? Because you are telling that P1 is true, and in the second step you are showing that for any number k, if P of k is true, for P of k plus 1 is also true. Okay, so P of 1 is true, so the next one will be true, which is P of 2. And now you show that P of 2 is true, so again the next one is also true, so P of 3 is also true. And then now if P of 3 is true, according to the second statement, P of 4 is true, and etc. and etc. So that is actually the idea of mathematical induction. And it is clear that it only works if you have a statement regarding a natural number. Because in natural numbers, the next number makes sense. But if you are working with real numbers, if I say square root of 2, I cannot say what is the next real number after square root of 2. It doesn't make sense at all. So this is a very, very powerful tool, as you will see. And then, yes, I usually start with a different example, but I want to follow exactly the sections in the book. So let me give you first a very simple example here to understand the method. Okay, so I would say that example. Show that for all real numbers, for all natural numbers, n 5 to the power of n minus 1 is divisible by 4. Okay, I want to make it very clear here. So what is my statement here? So let us understand the statement. Of course, you don't need to write all these details, but I want you to understand that I am following exactly what I have written on the board. So if I ask you, what is your statement here? P of n is this statement. 5 to the n minus 1 is divisible by 4. We are claiming that this is true if n is natural number, but we don't know. But at least you understand that by reading the text, or the problem, you realize that your statement is this one. This is the statement we want to show. It is true. And one method to think about this is mathematical induction. Why? Because this is a statement regarding a natural number n. Yes? So whenever you have some statement to prove which is related to the natural number in some way, one very strong method to think about is mathematical induction. I want you to get used to this way of thinking. Of course, I'm not saying that mathematical induction is the only way. Maybe there are much simpler, easier ways to do this. But mathematical induction is actually one very important tool, effective tool in our life. So this is the statement. Any questions regarding my statement? The first thing that I have to check manually is the truth of the same statement for n equals to 1. Okay? So the first thing that you do, this is called the inductive base, if you want to write. This is my base. I have to check it manually. So what does it mean? It means that I have to write the statement for n equals to 1. Okay, so I would write p of 1 and I read it again. But when I write p of 1, it means that I am replacing n with 1. So if I read it, it becomes pi 5 to the 1 minus 1 is divisible by 4. Okay, is this a statement true or false? 5 to the 1 minus 1 is indeed 4, and 4 is divisible by 4, so that's a true statement. True. But now, we assume that, I would say that let k be a natural number. Such that p of k, what is p of k? P of k means replace n with k everywhere. Yes? This is called inductive hypothesis, yes? We assume that this is true. No one guarantees that this is true or false. I myself assume that this statement is true for a natural number k. What I want to show is that if I assume that this is true, inductive hypothesis, I want to show that this statement will be true for the next natural number, only for the next one. Yes? So what I want to show, we show that p of k plus 1, what is pk plus 1? It means replace n with k plus 1 everywhere. Is true. So this is inductive conclusion. Yes? So I haven't done anything actually at all, but I want you to understand the format of thinking about it. If you really want to write it in a proper way, you have to write it in this way, or of course in your own language, but you have to respect to mention all of these things. So let me just repeat it here again. So I give you a statement, and you see that this statement is a statement regarding the natural numbers. One method that should come to your mind from now on is to use mathematical induction to prove that statement. and then you have to follow some rules. The first thing is that to understand exactly your statement. So at least even if you don't write it explicitly, I want you to think about your statement exactly. So 5 to the n minus 1 is divisible by 4 is the statement that I am claiming. I want to prove that, yes? Then you check that this statement is true for the first natural number 1. So you need to write P of 1. P of n is this statement. P of 1 means go and replace n with 1 and read it again. So then it becomes 5 to the 1 minus 1 is divisible by 4. Check if this statement is true or false, which is always very easy actually to check. And then it comes that this is true, yes? It turns out that this is true. Now, this is important. You assume that k is a natural number, and you yourself assume that this statement is true for that chosen value of k. You might ask, how should I know that? I want you to understand this is not a cyclic argument. Yes? You might say that, okay, I want to prove that 5 to the n minus 1 is divisible by 4. Well, but what you have done is replacing letter n with letter k, and then you are telling me that assume that this is true. I want you to understand, I am not assuming this is true just it. I'm assuming that if this one is true for k, it goes for the next one. Yeah? If this is true for k, it will be true for the next one. I want you to understand there is no guarantee if this is true or false. I'm just assuming that if this is true, I want to explore its consequence of this assumption for k plus 1. And if it is possible, by assuming that this is true for k, I will be able to show that this is true for k plus 1. Then, because p of 1 is manually, we have checked that this is true, then it means that this will be true for every natural number. So I want you to understand the logic. There is no circular argument here. Is that understandable? Yes or no? Okay. Okay, so now my duty is to show that 5 to the power of k plus 1 minus 1 is divisible by 4. Why this is such a powerful tool in our hand? Because when I ask you to prove this, you have to find a way to prove it. You do not have any tools in your hand. But now I have a very important tool in my hand. I'm assuming that 5 to the k minus 1 is divisible by 4. What I want to do is, based on this assumption, I want to show that 5 to the power of k plus 1 minus 1 is also divisible by 4. At least I am not empty-handed, yes? Here I am empty-handed, I don't know where to start, but here at least I know. I assume that this is true. I want to go to the next step and show that the next one is also true. Is that clear? Yes or no? Okay, so I don't know. So then let us see. This part is actually, you have to be a little bit creative depending to the level of difficulty of the problem. But what is your suggestion here? I tell you that, I guarantee you that this is true. I just want you to show me that the next level is also true. Okay, so let me understand this. So when you say P of k is true, what does this mean? This means that 4 divides 5 to the power of k minus 1. Is that understandable? This is exactly the same sentence. This is written in English. I have translated it into mathematical symbols. Yes? So this means that 5 to the k minus 1 is divisible by 4. But do you remember number theory? When we say that this is divisible by that, it means there exists a q in Z such that what happens? The right-hand side is 4 times q. Okay, so this is nothing new. It is just the translation of inductive hypotheses in mathematical symbols. Now I want to go to the next step. I want to show that if this is true, 5 to the k plus 1 minus 1 is also divisible by 4. You have a lot of probably experience if you haven't forgotten yet. So we want to go from this equality to a quality which is related to this expression somehow. So what is the motivation? What should I do you think? This is my assumption. based on this assumption, I want to say something about the divisibility of this combination by 4. So it motivates me. You see that I have here 5 to the power of k, but here I want to have 5 to the power of k plus 1. So the most natural thing to do is to do what? Can you tell me? To do what? You have 5 to the k. You want to have 5 to the power of k plus 1. So what's the natural step to do? Just multiply by 5, yes? Let us see what happens. You multiply by 5. If I multiply this by 5, of course I cannot just multiply this by 5. I have to multiply both sides by 5. And then I multiply this in, so it becomes 5 to the power of k plus 1 minus 5, and then this becomes 20q. But you have enough experience. Of course, now I know something about this combination, which is divisible by 20, but I don't need this combination. I need this combination. So to get rid of this minus 5, I add 4 to both sides, yes? So what will happen? It becomes 5 to the power of k plus 1 minus 1 is 20q plus 4. Yes? And then it is easy now. So it becomes 5 to the power of k plus 1 minus 1. I factor a 4 out. It becomes 5q plus 1. Can I call this a capital Q and make sure that this capital Q is an integer? Yes. Because q was an integer. If I multiply it by 5 and add 1 to it, definitely this is also an integer. So what I have shown that 5 to the power of k plus 1 minus 1 is 4 times an integer. So this means that this number is divisible by 4. So this means that 4 divides 5 to the power of k plus 1 minus 1. So you see, it's a very strong tool, yes? It seems that I am using the problem to solve the problem. But I want you to understand that is indeed very, very logical. I don't know, is that clear? So I write an expression for the natural number. We don't know is it true or false. According to the problem, I'm claiming that this is true. Yes? I read the statement. 5 to the n minus 1 is divisible by 4. This is the statement claimed by the problem regarding the natural number n, and I'm supposed to show that this is true. Of course, there are some other ways to do it. Might be some of them are even faster. If you know, for example, how to factorize such an expression, it is completely immediate for me. So 5 to the n minus 1 can be factored as 5 minus 1 times something, and 5 minus 1 is 4. That's it. Okay? But that is problem, you need to know more. But here, you are somehow using the same problem to solve it, to solve the problem itself, you know? So you see, I'm saying that this is my statement, this is being claimed to be true. I just check it for the first natural number, and it is extremely easy. You take n away, put 1 there, you produce a new statement, just check is this a statement, is a true statement or false statement. In this case, 5 to the 1 minus 1 is 4, 4 is divisible by 4, is a true statement. If this is not true, forget about it, this is not correct. Yes? If that is true, then you need to go to the second step, and this you assume you take a natural number k, you don't specify it, you say that k is an arbitrary natural number. I myself assume that the statement that I'm going to show is true for that particular value for k. The only duty of me is to show that if this is true, this will be true for the number coming after k. Yes? Is that clear? So there is no guarantee this is true. I myself assume that this is true. But based on the truth of this one, I have to show it is possible to go to the next number. And if that is true, then I am done. Why? Because I did it for 1, I realized for 1 is true. Okay, this tells me that if P is true for K, you can be sure that P is true for the next number. So if this is true for 1, according to the second, it will be true for 2. And now it is true for 2, again I can go to the next step, so it is true for 3, and etc. and etc. So this I wanted to understand. Of course we have to do a lot of exercises to master this skill, but I want you to understand the logic of the mathematical induction. And it is really powerful, because usually checking a very specific case, a particular case of a statement is not hard. You just take it and put 1 there, and this becomes a much easier statement than the general statement. And then you have something in your hand. You are not empty-handed. You just somehow it seems like that you're using the problem to prove the problem itself. And the important thing for me to understand is that this is logic. It's logical completely. Yes. Do you have any doubt about that? Okay, so let me just do some more exercises. And I think the exercises in this part is actually very good in the book. So let me for example solve problem 2090 here. Okay. So I can write it here. So example, this is problem 2090 in the book. So you are supposed to show that it's very similar. Let me make it 20. Let us solve both of them. So this is easier probably. So 5 to the 2n minus 1 is divisible by 8. Show that 5 to the power of 2n minus 1 is divisible by 8. Okay, so again, I want you to practice that. So what is your statement here? You say that you say that P of n, my statement here is that 5 to the 2n minus 1 is divisible by 8. This is what I am claiming in this problem. So what I need to do, I need to check the truth of this statement just for n equals to 1 for the time being. So I would say that what is P of 1? It means that 5 to the power of 2, I replace n everywhere with 1, minus 1 is divisible by 8. Okay. Is this a true statement or a false statement? It's true, yes, because this becomes 2 times 1, 2, 5 to the 2, 25, minus 1 is 24, 24 is divisible by 8 is a true statement. Yes, so that's true. Now, in principle, you should write always this sentence, let k be a natural number such that this is true. But let me just write it shortly, so that I would write P of k. This is mathematics. This is the inductive hypothesis or assumption. So P of k, 5 to the power of 2k minus 1 is divisible by 8. So let me write assumed to be true. We want to show that the next one is also true, yes? Let me write this here. So pk plus 1 means to do what? Replace n in your problem with k plus 1. Okay? So this becomes 5 to the power of 2 k plus 1 in pairs of brackets, in a pair of brackets, and then you have minus 1 is divisible by 8. we prove this is true. If I have assumed that this is true. So is the structure clear now? So all the mathematical induction structures are the same. This is the structure that you have to have in mind. Okay, so this one was true. I myself choose any natural number, any arbitrary natural number k, and I assume that this statement is true. My duty is now to show that the next step is also true. Okay, so what should I do? For example, I can do the same thing. So I would say that you are telling me that pk is true. If I want to translate that into mathematical symbols, it means that 8 divides 5 to the power of 2k minus 1. What is the translation of this? You learned this before. So there exists a q in Z with what property? The property is that the number on the right is the number on the left multiplied by that q. Okay, now your goal, now you see that you are not empty-handed. You have equality, you have an equality in your hands. You want to show some equality related to this expression. It is stronger than starting it from the empty hand, yes? So what should I do? I want to go from this somehow to something related to this combination. So what should I do? Can you guess? What should I do? So what is this one? It is 2k plus 2. So it is 5 to the 2k plus 2. What you have is 5 to the power of 2k. You want to have a 2 there. So what should I do?
Multiply by 25.
By 25. So it means that I multiply everything by 5 to the 2, yes? So it becomes 5 to the 2 multiplied by 5 to the 2k minus 1 is equal to 5 to the 2 multiplied by 8 multiplied by q. But when I multiply this in, it becomes exactly the combination that I need, 2k plus 2. But unfortunately, I will lose that number, but you have enough experience by that. So 5 to the 2 is 25. I multiply it here, it becomes minus 25. And I hope that you agree that you have some experience. You really don't need to calculate this number. So this is just, of course, this is not hard to calculate, but what I'm saying is you don't need to. Okay, at least I have this correct, because I can factor a 2 out and then I will have this combination. But instead of minus 25, I want to have minus 1, so it is natural that if I add 24 to it, yes? So instead of writing this, I would write it as 5 to the power of 2 k plus 1. I add 24. I add 24 to both sides. Then this becomes minus 1. Why? What was the motivation behind that? Because I want to have that combination. So it was probably the most natural step to do. And then when I add 24 to the left, I have to add 24 to the right. So it becomes 25 times 8 times q plus 24. But what is my goal? My goal is to show that this expression is divisible by 8. So what I need is to show that the right-hand side is an integer multiple of 8, and it is clear, yes, isn't it? What you can do, you can factor 8 out. So this is why I really didn't need to multiply this. So I factor an 8 out. So then it becomes 25q plus 3. Yes, agreed? And now, can I be sure that this is an integer? Because if you go back, q was an integer, multiplied by 25 is an integer, add 3 to it is an integer. So if I call it q, I am completely sure that this q is an integer. So this means that, therefore, 5 to the power of 2 k plus 1 minus 1 is 8 multiplied by an integer. And this exactly means that 8 divides this combination. Yes? Is that right? Okay. Now I think another problem in the book, I see it is good. So let us, I want to write this one and wait a little bit for you so that you can struggle with it yourself and then we can solve it together. So that is a good exercise. Exercise 2091. I just write it here and wait for you. So exercise 2091. So let me write it here. Show that 3 to the power of 3 to the power of 2n plus 1 plus 2 to the power of n plus 2 is divisible by 7. Yes? I really want you to respect everything. First of all, try to write P of n as a statement. Try to write everything down to make sure that you understand everything. Then we come back and solve it together. Okay, did you get any answers? By the way, for me in this lesson, it's important to be able to write and understand. Of course, the other part might be tricky, so this is still mathematics, so you have to be creative and skilled to be able to do these things. But if you don't mind, let me solve this problem in 2 methods. One, today's lesson, mathematical induction, the other way, modular arithmetic. Okay, so there is, what I'm saying is that I want you to understand, if you have a statement that you are supposed to prove and it is regarding a natural number, then one very powerful tool that you have to remind yourself about is actually mathematical induction. But I cannot force you, unless in the exam I ask you to do it with mathematical induction. Yes? So here, let me solve it in 2 different ways. First of all, method 1, mathematical induction. So how should I do that? Okay, what is my statement? Let me be specific again. P of n, 3 to the power of 2n plus 1 plus 2 to the power of n plus 2 is divisible by 7. This is the statement that I am claiming to be true for every natural number. By the way, the statement that they write, okay, so they have written n belongs to n. So I should write, show that this is divisible by 7 for all natural numbers n. Okay, so now what you have to do is to start from the inductive base by checking that this is true for the first natural number 1. So then it means that you go here and replace 1, n with 1 everywhere. Okay, but is this a true statement or a false statement? If that's false, forget about that. That is not true. But if this is true, you have to go to the next step. So 2 times 1 is 2 plus 1, 3. 3 to the power of 3, 27. Plus 2 to the power of 3, 8. This becomes 35. So P1 is claiming 35 is divisible by 7, which of course is true. Yes? And now I assume that for any natural number k, for an arbitrary natural number k, I assume that p of k is true. So 3 to the power of 2k plus 1 plus 2 to the power of k plus 2 is divisible by 7, assumed to be true. Yes? And then we want to show that this statement for the next number is also true. So don't be sure that you don't make mistakes. When you write p of k plus 1, it means that, you have to replace k with k plus 1, and then make sure that you are not making mistakes. So this becomes 2. I replace k with k plus 1. I have to put it in pair of brackets, and then plus 1, and then I would write 2 to the power of k plus 1 plus 2 is divisible by 7. Yes? To be proven, yes? But before proving that, I recommend you to simplify your expression as much as possible. So then you multiply these two in. 2k plus 2 plus 1 is 2k plus 3. 3 to the power of 2k plus 3. And then k plus 1 plus 2 is 2 to the power of k plus 3. So you can forget about the original form. You can work with this new simplified form. But again, the story is the same. I start from this one. I assume that p of k is true. If I want to translate this in mathematical symbols, I would write it as 7 divides 3 to the power of 2k plus 1 plus 2 to the power of k plus 2. This means that there exists an integer q so that 3 to the power of 2k plus 1 plus 2 to the power of k plus 2 is actually 7 times q. This is now something in your hand. You have to somehow use this fact, which is assumed to be true, show that this expression, which is slightly different from what you have in your hand right now, is also divisible by 7. Okay, so do you have any suggestions for me to do? I want to start from somehow this equality, and by mathematical arguments reach to something which is somehow related to this expression. So I don't know. Do you have any suggestions? Was it hard? Yes, Ruben?
I mean, I don't know if you can solve it with this, but you can multiply with 3 to the power 2.
Let us yeah, that is probably the way that I wanted to follow, even though I couldn't see until the end of the problem. But let us see what happens, yes? So what you're suggesting is, because I have a power of 3 here, but I have a power of 1, so it is a good step to multiply everything by 3 to the power of 2. At least it will make this one right. Yes? So then I multiply this expression by 3 to the power of 2. Then this becomes 3 to the power of 2k plus 3. But then unfortunately this will change a little bit. So 3 to the power of 2 multiplied by 2 to the power of k plus 2. And then of course 3 to the power of 2 is 9. So you can write 9 times 7 times q. Okay, so this is good, and hopefully by the experience you have gotten so far in number theory, you shouldn't be that worried about the form of the right-hand side, yes? You don't want to optimize it. What you need is to have a factor of 7 at the end. For the time being, I have that factor of 7, so I'm not worried at all. But the point is that if I look here, I have two problems. First of all, the coefficient here is 1. Unfortunately, I have 3 to the 2 there, which is 9. And of course, then I will have an exponent k plus 3. Still, I have my exponent k plus 2. Okay, it's not that hard to understand what to do now. What should I do? Let me copy and paste this part, which still I need. Okay, this is 9. I want to have an extra power of 1 here, so I need a 2. Yes? So what can I write? This is 9. I want to have a 2. So what should I write? Instead of 9, I can write what? 2 plus 7. Yes? And then multiplied by 2 to the power of k plus 2. On the right hand side, I have 63. This is very simple here, so let me just multiply. Yes? And then what I do, I multiply this thing, I distribute. So it becomes 3 to the power of 2k plus 3. And then I multiply 2 by that one. It gives me exactly the combination that I need. But of course, I get some extra information, some extra term that I don't need. But if you haven't forgotten what you have studied in number theory, this wouldn't be a problem for you. Because that's exactly 7 times something. And then I have here 7 times something as well. Yes? So it means that I can move this to the other side. And then I have this combination. Yes? 3 to the power of 2k plus 3 plus 2 to the power of k plus 3. I keep 63q there. I move this to the right hand side and I make it negative. Yeah, so you had some experience of this type of calculations before. So then what happens here, it becomes 3 to the power of 2k plus 3 plus 2 to the power of k plus 3. And then what I can do, because I need a factor of 7, and then both of them contain a factor of 7, so I can factor it out, it becomes 9 times q minus 2 to the power of k plus 2. And what I need is I want to make sure that this is left, what is left over here is actually an integer. And is it an integer? Yes. Because q was an integer. Where was it? Yeah, here. Q was an integer. So if I multiply it by 9, this is an integer. K is a natural number from the beginning. And 2 to the power of k plus 2 is also an integer. Better to say is a natural number. But the difference of an integer and a natural number at the end is an integer. Yes. So this number is an integer multiple of 7. So this means that a 7 divides 3 to the power to the power of this plus 2 to the power of k plus 3. And this means that p of k plus 1 is true. So you see, I started with this assumption that p of k is true. And after all these calculations, I concluded that p of k plus 1 is also true, so they are not done. So this is one way to do that. Of course, if I ask you to do it using mathematical induction, you have to do it in this way. But if I just ask you to prove it, there's a better way to do that, and that is a modular arithmetic. So let me write method 2. Okay, do you want to give it a try yourself first? Because you still need to know this until week 51 that you have the exam. Yes, so I would write method 2. modular arithmetic. Okay, so you can think about it until I'm just cleaning the board. Do you remember, if you want to show that a number is divisible by another number using modular arithmetic, what you need to do? For example, you want to show that m divides a. You want to show that a is divisible by m using the tricks and techniques of modular arithmetic. If you remember, this is equivalent if this is natural and this is integer. You remember? This divides that if and only if a is congruent to 0 modulo m. So if I want to show that a number is divisible by a natural number, one way is to use this symbol and the properties of this symbol, or you can equivalently translate it into the congruency language and use the tricks and techniques there to prove this. So remember, we had this before. If you want to show that a number is divisible by m, I would recommend you to always think about this way of doing it. Is that understandable? Because what was the definition of congruency? This means that m divides the left-hand side minus the right-hand side. But the left-hand side minus the right-hand side is just a. This means that m divides a. Yes? So here, if I want to prove this claim, I have to show what? So this is the claim. I want to show that this number is divisible by 7. Yes? So instead of showing it using mathematical induction, I can show that this number is congruent to 0 modulo 7. Yes? So that's also completely true. So I need to show that 3 to the power of 2n plus 1, and then I have plus 2 to the power of n plus 2. I want to show that this is congruent to 0 modulo 7. This is my question mark. If I can show this, we are done. And actually, you see, this is much faster. Okay? But you have to be sometimes a little bit creative. In mathematical induction, you really don't need to be that creative because you have something in your hand you start with, yes? But here you have to be creative. Not that much, by the way, here. This is not hard. Can you tell me what to do? I want to show that this, whatever n is, if n is a natural number, this is congruent to 0 modulo 7. You have to think a little bit about what you have learned before, yes? Any suggestions for me? Yes?
3 to the power of 2 is 9.
Yes?
In module 7, that's 2.
Yes? So you have to, yeah, but this is not 3 to the power of 2. I have to write it in a way that I can use that. Thank you. So what we do, I would write 3 to the power of 2n plus, is that right? Yes. Plus 1 plus 2 to the power of n plus 2 is congruent. So I need to continue. I write the modulo 7. I rewrite this as actually Dima mentioned. So I would write it as 3 to the power of 2 to the power of n multiplied by an extra 3, yes? I hope that agree that this is the same expression here, and then might be I can also do something like that, or I can keep it for the future. I can write it here now. So I can write it as plus 2 to the power of 2 multiplied by 2 to the power of n. Okay, but 3 to the power of 2 is 9, and then to the power of n multiplied by 3, and then I have 4 multiplied by 2 to the power of n, modulo 7. But I told you that the important thing about modular arithmetic is that whenever you have a base which is larger than the module, it's always better to simplify, yes? So there is a better name for 9. If I want to work with the module 7, instead of 9 I can write 2. Why? 9 is 2, because 9 minus 2 is 7. 7 is divisible by 7. So instead of 9, I can write 2. So then it becomes, let me write 3 on the left if you don't mind. And instead of 9, I write 2 because I am working in this module. And then I cannot do anything with the power, I have to keep it. And then I don't do anything with this one because 4 is still lower than the module. So it becomes this one. Yes?
Then we can factor out to the power of n.
Or you can say I have 3 of them, I add 4 of them, so it becomes 7 of them, yes? So it becomes equal to 7 times 2 to the n modulus 7. But then 7 in its own module is 0, yes? Because 7 minus 0 is divisible. So instead of 7, I put 0, and then I multiply it by n, 2 to the n, and then you know that this is exactly 0 modulus 7. Okay, so this is much faster. Of course, I wrote a lot to elaborate it for you, but this is probably faster than mathematical induction. But this doesn't understand, actually, you shouldn't underestimate the power of mathematical induction, especially if you have to be very, very creative. Any questions here? Okay, so this is some questions that we had. I think there are also some, I don't know, in the body of the text, they have some questions, but I don't see any exercises related to that. So let me solve one of the problems in the text itself. Okay. So let me write this. But they are starting from a 0. I want to. Okay, so let me write it in a similar form. So I would say, let A sub n be a sequence defined recursively as follows. We know that A1 is 2, and we know that AN is AN minus 1 plus 3 if n is natural and if n is greater than or equal to 2. So you see, this is the recursive way of defining a sequence, yes? I am just giving you the first term, but I am not giving you the general term for an. I am relating the n, the nth term, to the previous term. So that is recursive way of defining, if you remember. Okay, show that an is equal to 3n minus 1 for all n in n. Yes, is that clear? So I have defined you a sequence in a recursive way, and I ask you to show that a sub n, I'm claiming that the nth term is this one, okay? And I want to show that this is indeed the case. Okay, so how should I do that? I want to use mathematical induction. So can you tell me what is P of n here? Because you need to understand, even if you don't write it, but you need to understand what is P of n. So P of n is your claim about n. So here, what is my claim about n? My claim about n is that a sub n follows this rule. Yes? So I would write that a sub n is 3n minus 1. This is my claim. Then I have to show my claim is true. If I want to use mathematical induction, which is not the only way, by the way, here even you can do it faster. But let us practice mathematical induction. So P of 1, I have to check it manually. So it means that I replace n with 1 everywhere in my statement. So it becomes a sub 1 equals to 3 times 1 minus 1. So this is equivalent. Simplify this. A sub 1 is equal to 3 times 1 minus 1 is 2. A1 is 2. Is it true or false? It is true because A1 is given to be 2. Yes? So that is true. This statement is true. Then I myself assume that K is a given natural number, whatever it is. I assume that P of K is true. It means that A sub K is equal to 3 times K minus 1 for a given natural number K, assumed to be true. Sometimes I doubt, is assumed with one M or double M?
I think it's 1.
1, I think. Okay, so I'm just writing it all, I don't know. I got suspicious a little bit now. P of K plus 1. What is P of K plus 1? It is A sub K plus 1. I replace K everywhere with K plus 1. So it becomes 3 times K plus 1 minus 1 to be proven. But I usually told you that it is better to simplify your expression as much as possible and then start proving it. So what I do, I simplify my expression, which I'm supposed to prove, and that is A sub K plus 1 equals to 3K plus 3 minus 1, which is plus 2. Okay, so I know that I am assuming that A sub K follows this rule. I want to show that A sub K plus 1 will follow this rule. If I can show that, then I am done. Okay, but how should I start? Here, it is better to start from this one. So you see the nature of the problem is in a way that I start from here. I want to show that AK plus 1 is this one, so I would write the left-hand side here. The left-hand side, which is A sub K plus 1. I want to continue and show that this one is equal to 3K plus 2. But this equation is true whenever n, the index, is a natural number and the index is larger or equal than 2. So do you think that I can use this one for, can I use this for A sub K plus 1? The answer is yes. Because what was K? K was a natural number, so it means that the minimum value for K is 1. And then K plus 1, the minimum value becomes 2 and natural. And this formula works if n is natural greater than or equal to 2. So that's completely valid. I can use this formula if I want to. So this tells me that whatever n is, you can use this fact. So instead of n, I replace it with K plus 1. So this becomes A K plus 1. I am just replacing n with K plus 1. This becomes K plus 1 minus 1. And then I have a positive 3 at the end, yes? But then K, this is K plus 1 minus 1, nothing except K plus 3. But I have an assumption about a K. And that is equal to 3K minus 2. So I replace this, I use that fact and put it here. So it becomes 3K minus 1, but I have plus 3 at the end. But minus 1 plus 3 is how much? Is exactly 2. Is exactly 2, and that's exactly what I want to show. So the left-hand side of this expression is equal to its right-hand side. So you see, it was a different strategy here. In the previous examples, I started from my assumption to conclude something about my conclusion. But here, the nature of the problem was more or less an identity. If I want to show an identity, I should start from the left-hand side usually and simplify it so that I can reach to the right-hand side. But in the way that I wanted to do this, I had to use somehow my assumption. Otherwise, I will stuck here. I would not be able to continue. But now I could continue, and that is my formula. If you remember, I was talking about the Fibonacci sequence, and then we realized that the general formula was a little bit hard. And we checked it for, I think, 2 or 3 numbers, and we realized that formula was correct, at least for that one, but that is not a proof. But now you can, in principle, prove it. Okay, so if I remember the formula correctly, so let me see if you agree with me. If you have your notes available, I would appreciate if you go back and check that formula for me. If I am making any mistakes, please let me know. So here, I think, do you remember the Fibonacci sequence that we defined recursively? Let me call it F. F1 was defined to be 1. F2 is defined to be 1 again. And then we define any term from the third term onward. It's equal to the previous term plus the previous term. Yes, that was the definition of the Fibonacci sequence. Do you remember? So if I want to write some of them for you, the first one and the second one by definition are 1, but from the third one onwards, you have to add the 2 previous ones to get the new one. So 1 plus 1 is 2. And for the next one, I add these 2, it becomes 3. For the next one, I add these 2, 5. Add these 2, 8. And then, I don't know, 13, 21, etc., etc. It seems that it's a very random sequence, but someone was able actually to find, I don't know who, but there is a method to describe this and find the formulas. But for the time being, if I am right, so that would be something like this. Claim is this now, that the nth term, it's completely counterintuitive, because all of these numbers are very nice and natural numbers. But it turns out that if you want to have a formula that generates this sequence term by term without ignoring even one single of them, the formula was a little bit complicated, and it was related to the golden ratio somehow, yes? So I think it was my 1 plus square root of 5 over 2 to the power of n minus 1 minus square root of 5 divided by 2 to the power of n. That's it, I think so. Let me check it. For example, it's very strange, yes? Because the square root of 5, it seems that when I'm raising to powers, of course, there will be a lot of square root 5s left here. And the same thing here. But somehow, surprisingly, they will cancel out somehow to generate these terms one by one. For example, let me check. For n equals to 1, this is 1 plus the square root of 5 divided by 2, and then yes, it becomes 2. Yes, that's correct. Because you see, if I put 1, it becomes 1 plus the square root of 5 divided by 2 minus 1 minus the square root of 5 divided by 2. And then minus 1 and 1 cancel. 2 square root of 5 divided by 2 is the square root of 5, and that will be cancelled by that one. You get 1. Yes, if you remember, we checked that for some of them. But now, we cannot trust on this formula. Who knows that? I think we calculated up to 2 or 3 terms, and it was right. But then how can I be sure that this really generates this sequence one by one? Okay? And that is what I want to tell you. This is also weakness of mathematical induction. Because if we don't know the formula, we are not able to prove something. So that is called, I will call it the weakness of mathematical induction. So if you want to prove something using mathematical induction, you should have the statement in front of you as a proposed statement. What you can do is show that yes, this statement that is being claimed is true. But if you don't have the statement, you don't know what to do, yes? If I don't give you this formula, there's only one way for you to be so smart to generate a formula yourself. Of course, you can just do some random work and try to guess the formula, and then after guessing the formula, then you can use mathematical induction to really prove that the formula is correct. So be careful about this. If I want to use the mathematical induction, I should have my statement, the full statement in front of me, and then I am able to show that this statement is true using mathematical induction. So I don't know how big trouble will be this for us. I haven't done that before, but let me at least start understanding this a little bit, yes? So if you want to prove that this formula is true, what I'm supposed to do, this is my statement. So the statement is that f of n is equal to this if n is a natural number. This is my p of n. Yes? So our claim is that this will generate the Fibonacci sequence, term by term. So I have to check p of 1 manually first. So it means that f of 1 is equal to square root of 5, and then I have 1 plus square root of 5 divided by 2 to power 1 minus 1 minus square root of 5 divided by 2 to power 1. This is what is claimed by p of 1. But you need to check, is this claim a true claim or a false one? But then I check that one here. This is equivalent to saying that f1 is equal to 1. If you calculate this, it's a very simple calculation. It gives you that f of 1 is 1. But is this statement true? Yes, because by definition f1 is 1. So that is true. Yes? The second statement, the second part is in the inductive hypothesis. So I assume that p of k is true. What does it mean? It means that I assume that for a given natural number k, this is true that f sub k is equal to this number. Assumed to be true. Yes, this is assumed to be true. What I need to show might be, it is hard, I don't know. We have to show that f sub k plus 1 is equal to 1 over square root of 5, and then you should write this one to the power of k plus 1 minus 1 minus square root of 5 to the power of k plus 1 to be proven. So if I can do that, then I am done actually. But it is better than nothing, but it is different from discovering the formula. Is that understandable? So here, the formula is discovered by someone, and you are supposed to check it. But don't underestimate this. Because if you calculate this even for 1 billion terms, and this is true case by case, there is no guarantee that it will be true for the next one. But by mathematical induction, this is completely guaranteed if I succeed to go from this one to this one now. Okay, what should I do you think? Yeah, we have a little bit of time. I think we can finalize it if we do it fast and if it is not a nasty problem. I haven't done that before, but I don't think we will face big problem here. Let us see. So what should I do? I start from the left-hand side of this. So the left-hand side, is f sub k plus 1. But, okay, you cannot do that. I realize that because it needs another, yes, I remember right now, it needs another mathematical induction which is called a strong mathematical induction, and that is not part of your lesson. At least this is not a very bad example. You will understand why. Why I cannot use mathematical induction in the version that you have read so far, you studied so far for solving this problem? So at least this is a very good take on from this example. It can be shown by mathematical induction, but it is called a strong mathematical induction, which is a slight modification of this version that we study here, and you don't study it. But I want you to understand why your mathematical induction is not enough to prove this. This I want you to understand. Because what can I write for f sub k plus 1? Can you help me to write something for it? The definition of the Fibonacci sequence goes from here, yes? So what can I write for f sub k plus 1? Can you help me? What should I write in front of it? F sub what? What should I write? F sub k plus, what should I write? K minus 1. Okay. Now, do I know something about f sub k? Do I know something about f sub k? Yes. Assumed to be true. I know something about f sub k. But do I know something about f sub k minus 1? The answer is no. Don't think that you know it. You can replace k with k minus 1. The whole logical structure will collapse, yes? So this logical structure tells you that if you assume that p of k is true, you prove that the next one is true. Yes, but you need more assumptions. Here you need to know if p of k and p of k minus 1 are true, and then might be you are able to get the conclusion that p of k plus 1 is also true. So you see, you need more assumptions. Only the previous assumption, the previous step will not help you to do something for fk plus 1. You need to know something, not only for the previous step, but for the previous step. And you don't have it here. You only have this assumption for f sub k. So this is why using this version of mathematical induction, you will not be able to prove this. But it can be modified very easily so that you can have another mathematical induction is that to check everything manually up to some point and show that based on all of them the next one is true. And then you can also conclude that everything is true. But at least I want you to understand that this is not possible using this version of mathematical induction that we have. Because it needs two assumptions. One assumption related to the kth step and one assumption related to the k minus first step. The assumption for the kth step we have, but the assumption for the k minus first step we lack. So we cannot do that. It doesn't mean that the whole mathematical induction will collapse. Mathematicians have actually extended that and modified that to consider these cases as well. Okay, so I think that's a good point to stop here. No questions? Thank you very much. And by the way, outside is minus 14. It's nice, yes?